Thank you very much for the introduction. And I'm an engineer. It was great to see Peter's talk, to see another engineer out here. This is going to be a little bit different. And I do have to apologize. I kind of changed my talk up a little bit at the last minute. So a lot of what I do is very technical and it can be kind of boring sometimes. So I actually picked a project that we've been working on in children, another project that was funded by the MCHRI, to just kind of give you a feel for some of the stuff that we do and some of the interesting things that go on. So what I'm showing you here is, so this is actually an image of a rat brain, and the white parts of the image that you see are actually the blood vessels in the brain of this rat. And what you're looking at is something called a functional ultrasound image. So it's like fMRI, except for where parts of the brain are activated. We're measuring that with ultrasound, and you can see this is from whisker stimulation in a rat. You'll see parts of the brain light up, and you can actually watch these things happen in real time. Now, of course, ultrasound is one of these modalities that actually doesn't go through the brain, go through the skull very well. So in this particular image, which is from a group in France, they actually had to remove the skull of the rat. So, of course, we don't want to do that in children. But just to kind of give you a little bit more information about what they do, essentially they kind of rely on some of these interesting techniques that we have in ultrasound. These new and sort of exciting technologies that you guys obviously don't really see until you get to the end result. But at any rate, they've showed some really exciting results. So, my lab had been working on Doppler imaging technologies. So, we thought we would, try and improve upon some of these things. So, just to give you an idea of how functional ultrasound works, like fMRI, functional ultrasound really operates on this idea that you're using some sort of vascular measure as a proxy for brain activation. So in fMRI, this would be something called the BOLD response, the blood oxygen depletion. In ultrasound, what we actually look at is a change in the blood flow. So whenever you have an activation in the brain, you get an increase in blood flow in that area. And so we can, with very sensitive Doppler techniques, we can pick up on that blood flow and we can see where these changes in activation occur. So in functional ultrasound, we use a measure called a relative blood volume or a cerebral blood volume, and we get that measurement from a not commonly known technique. To radiologists, when you say can we look at the blood flow, they'll turn on a mode they call Doppler imaging or color Doppler imaging, and it's usually you'll see that as kind of red and blue blood flow in the image. But there's another mode out there, it's called power Doppler imaging, and it's actually much more sensitive to the blood flow, and it doesn't give you any directional or speed information. It just tells you whether or not blood flow is going on. So here's just a tiny example of what power Doppler imaging is, and these images commonly look like this kind of red-orange map, as you see here. And what we have going on here is you put an ultrasound transducer on the fontanel of a neonate, and you can make images of the blood flow in that brain there. And then you can do some interesting studies where you look at the variation in the brain activity. In this particular study, they were looking at the children when they had quiet and active sleep. Okay, so if you're trying to measure blood flow in the brain, I kind of compared the different characteristics of imaging flow in the brain of a neonate to that of an adult human in their liver. So when you image a neonate, you're looking at target depths that are maybe a millimeter to 10 centimeters deep. In the adult liver, you're going much deeper than that. You're looking at 10 to 20 centimeters depth. The vessels in the neonate brain are much, much smaller than that in an adult liver, so on the order of a hundredth of a millimeter to a millimeter. And then the velocities of the blood in the brain of a neonate is much, much slower. So that affects the settings on your ultrasound scanner, and it affects them in a way that kind of your conventional ultrasound scanners that you might use to image fetuses, the scanners that you find in the OBGYN clinics don't have the capability to image that. And so for the neonate brain, we have to go to much higher frequencies than you would typically use for fetal imaging. So here we want to operate in the 7 to 15 megahertz range. So as a comparison, in your adult liver, normally we use 2 to 5 megahertz. That's the same for OBGYN cases. We'll typically be in the 2 to 5 megahertz range. And then I'm going to kind of get into this idea of snapshots. Typically to make images in the adult, we want to capture 8 to 32 looks at a particular direction in order to measure this blood flow. But to do this in the brain with high sensitivity, we need 1,000. We may need up to 1,000. And so when you kind of change these parameters and you start to look at the data burden, how much data you need to make this quality image, all of a sudden you're looking at 80 times the normal amounts of data. So I kind of like to say that in ultrasound, we were actually the first big data people. So you can actually generate on the order of gigabytes per second of data with ultrasound. Okay, so I kind of let you know a little bit about this power Doppler imaging that we use, and what power Doppler is really just it's a fancy motion detector. That's all it is it detects motion, and when you make the image, just things that move faster show up brighter, things that move slower are a bit darker, and so this is. What you see here, this is what your typical Doppler data looks like, and so this is kind of the depth into the image, and then this axis here along the bottom, that's time. So what you're actually doing is repeatedly looking at a particular location with your ultrasound. So you're sending in a pulse and you're getting in an echo, and it's kind of like with a camera. If you set up a long exposure time, you can get very sensitive light detection at a particular location, and the same thing is true for ultrasound. So the longer you look at a particular location, the more sensitive you are to that flow. Okay, but the problem is that the echoes from tissue are much stronger than that from blood. And so what happens is when you look at a location, so if you look at this data here, it just looks the same all the way across. Okay, and the reason for that is the echoes from tissue are so strong, it obscures all the blood signal. So what we need to do is we need to eliminate that. So what we do is if you go ahead and filter that out, you can then see the underlying signal from the blood. So now you can see motion of that blood. That blood is moving in a particular direction. Okay, so that's your quick basic on power Doppler imaging, but there's a lot of challenges with respect to power Doppler, and so these are some of the challenges that we are going to address. In particularly, power Doppler it becomes much more challenging at these slow flows. You have slowly moving tissue, which then kind of looks like blood. You have these other problems. The electronics of the ultrasound system will give off noise itself, and so you have to worry about that. And particularly, the one that the radiologists hate the most are these things called motion artifacts, or they call them flash artifacts. So if you're scanning with your transducer and then all of a sudden you move too quickly, then the system thinks that blood is everywhere and it flashes up as a big red blob, and then you can't see anything. So this particular imaging mode is very sensitive to motion. And for these groups that are doing functional ultrasound, if you have any type of motion, it will kill the whole functional imaging. So a lot of times they put on these things called a baby bonnet. So they'll strap a bonnet to the neonate and they'll stick the transducer so it's fixed to their head. So it's not very comfortable, and you don't have the ability to kind of freehand put the transducer where you want to image. Okay, so how do we overcome a lot of these challenges? So we use two technical innovations, and one is we switched to a very high frame rate imaging modality. So if you kind of think back, your typical OBGYN imaging system runs at about 30 to 60 frames per second. So what we need to do is we need to up that frame rate and get upwards of about 1,000 frames per second. So in order to do that, we have to give up some of our image quality. And so we use a technique that's called Ultrafast Doppler. And the other technical innovation is we, instead of looking at echo strength, we've kind of looked at some of the other properties of the echo. And I won't bore you with all the technical details, but the one that we particularly use here is something called spatial coherence imaging, where we look at the echoes that come back. We look at how similar they are rather than the echo strength. So that has the ability to suppress a lot of the noise and the motion that we encounter. Okay, so because we can't implement this on a regular ultrasound scanner, we have to build our own. So that's commonly what my lab does. So we grab this thing called a Baris Onyx, which looks like this steel box that you see here. And this is really just an ultrasound front end. It allows you to transmit and receive those echoes. And then we attach a bunch of stuff to it to allow us to make the images. So we can execute these ultra-fast sequences that have just 7 transmits per image frame. And so we can pulse this or get image frames at a rate of about 2,100 frames per second. So what we'll do in these movies that I'm about to show you is we capture 10 seconds of data, of a continuous data dump. And so essentially our Doppler interrogation is running at about 300 hertz. Okay, and so then we captured a bunch of neonates through the fontanel, and here are some of the images. So here you're looking at a quote-unquote real-time video of a neonate through the fontanel, and what you see on the left here is this is the ultrafast Doppler, and then we kind of add this what's listed as a SLAC component. This is our spatial coherence component. So you have technical innovation 1, and then the combination of the 2 right here. And so immediately what you see when you add that spatial coherence component is you can see a lot of the motion artifacts. That blurring of the blood vessels goes away. And you're able to see a lot of these very tiny vessels on the order much smaller than a millimeter. You can see them up here, some of the peel arteries and some of the other arteries going on. This is just another snapshot. Again, this is a 10-second video, so we've captured 3,000 snapshots here, 3,000 frames. And we can do interesting things like we can look at particular blood velocities. So in this particular case, we're showing all the blood velocities that are above 8 millimeters per second. Okay, and so one of the things that we have to do is make sure that the blood measurements that we're using when we do these special new techniques, that they're actually related to a physical parameter. So in this case, what you see here is just 3 snapshots in time. Here's the video down here, and what we show is this is the blood flow image. This is actually the B mode image. This is through the fontanel, and this surface that you see here is just it's the top of the brain. And so here, what we've done is we've set up a measurement of the blood vessel in that area, and we're tracking the blood flow as a function of time. And I think this video stopped playing, but at some point the baby begins to start sucking on a pacifier. And so it's more correlative. It's not exactly a direct consequence, but as that baby began to start sucking on the pacifier, the blood flow in that region shot up. So you can see that right along here, and then the baby stops and the blood flow decreases. Okay, so that's kind of the new technology that we've developed, and the nice interesting thing is that it's not just applicable to imaging in baby brains, but we've found other uses for it as well. So I have a project that's funded by the NICHD that I was working with the OBGYNs on, and we decided that the technology was good enough that we needed to switch what we were doing in that project and begin to use this technology. So we have this project, which is to develop new tools for placental structure and function as part of the Human Placental Project. And the idea was to go after these spiral arteries that develop and look at the spiral artery remodeling process in the placenta. And so these results that I'm about to show you were actually just taken this week. So I think Tuesday or Wednesday this week, sort of our first images we finally got from this project. And so what you're looking at here is the blood vessels in the placenta. This is what we believe is the chorionic villi right here. So it's sort of the first visualization of these villi in high detail with Doppler ultrasound. So it took us about 1/3 of a second to capture this image. And so the image on the right here is just sort of the B-mode image where we have the data overlaid. And since this is brand new data, we haven't had a time to sit down and optimize the image quality. But we were very excited to see that we were able to see this structure within the placenta that hasn't been able to be seen before under ultrasound. So that's all I have for you. I just wanted to do a big shout out to my collaborators with respect to the neonatal brain. Marco does a lot of the work, the technical work, and Jason and Erica are our clinical collaborators. And then on the placental imaging, Leo is our technical lead there, and we get a lot of help from the OBGYN folks, Virginia, Deirdre, Anna, Amin, and Jane. So thank you very much.
We have a couple of minutes for a question, if anybody would like to ask. If not, I'll ask one question, and I'll just speak from here. Is that your tip proposal was to try to ultimately develop a whole body scanner. The technology that you've spoken about, how does that work where you have air? I'm a lung doctor, so I've sort of...
So for the whole body scanner, the idea is you would put a child in the bath instead of through the air. And so the big thing for ultrasound, of course, is coupling the energy from the ultrasound transducer to the body. And so when you have air, you can't couple that energy. But if you have a liquid medium, typically when you do an ultrasound scan, you have gel. In this particular in the case of the body scanner, you would have sort of a water medium, a water bath, which would, hopefully is more comfortable than sticking a child in a
So even
MR
though there's
tube.
air in the lung and air in the bowel, you would still be okay? Or?
Oh, so for that you would still be okay because the imaging techniques that we're using are actually from geophysics. So they do this technique called full waveform inversion, and we are able to look at the body from a number of different angles, so then you can you can actually get the energy to penetrate from different angles.
So that's why we have multiple schools involved. Dr. Ariano?
Great work. My question has to do with you mentioned thermal noise.
Yes.
And I'm just wondering what the boundaries are you have between getting a stronger ultrasound versus having an impact on the tissue. And I wonder how it relates to Dr. Thakor, who was presenting earlier. I don't know if you were here during his talk, in which he was using it to activate the pancreas to try to get the mesenchymal stem cells somehow activated within the tissue of the pancreas for regeneration. So although he didn't go into it, I would guess that it probably had some physical effect on the pancreas itself.
Yes. So all of what you're asking is essentially related to what we call the intensity of the ultrasound. So how strong are the pressure waves that you're applying to a particular area. So when you go to diagnostic imaging, the FDA regulates the amount of acoustic energy that you can apply to the tissue, and especially when you're imaging fetal tissues. There are even additional guidelines that are applied, so you cannot exceed a particular level. The other thing to keep in mind is the pulses, the length of the pulses that you transmit into the body are much shorter for imaging. So the idea is in imaging you want a very short pulse, but when you use the pulse focus ultrasound, the therapeutic ultrasound, as we say, you can use much longer longer pulses. So in the case of the thermal noise, you can increase the amplitude of the pulse, but because it's so short, the amount of energy that you're dumping into the tissue is not strong. It's not a whole lot, so you don't heat up the tissue, you don't cause any mechanical effects. When you increase the intensity and you increase the length of the pulse, then you begin to create these pressure field gradients across the tissue, and you cause the cells to be stressed, and that's what's causing the cells to release all sorts of cytokines. Sorry, the cytokines are not my area. But that's sort of it becomes, when you increase that pulse length, you then begin to create mechanical stresses on the cells, which you don't do with
So you have all these
diagnostic pulses.
technical capabilities which you can control, basically.
Exactly. Yeah.
Okay.
Thanks.
Thank you very much, Dr.